Okay guys, so this is the last part of the video and we're going to have a look at the results. So first we can have a quick look in Fluent itself in the Post-Processing tab. We can check a few important things, like we can create a new contour of, let's say, pressure's fine, we want pressure coefficient. And we want to do that on the surface body. Oops, sorry, all of the interior. So we can see here that we got a pressure coefficient, well, the highest pressure coefficient, and that should theoretically be 1. If we look up there, it's 9.86 or something, if I read that correctly. So we know that that part of the solution is good. We got low pressure regions here on top of the aerofoil, which makes sense because we're getting the flow accelerating over there. It's a symmetric aerofoil, so the top part matches the bottom part, which also looks pretty well on. And it looks like we got some stagnation point here as well, which is what we would expect. We can go one step further and look at velocity on the velocity magnitude. So we can see here that should be 0 velocity because it's our stagnation point, which we can see. We can see that the velocity increases above, so 30 meters a second is about orangey, which should be the whole kind of domain, which it is, and then we can see this location of flow acceleration, which is what we would expect as well. We can see the flow kind of loses a bit of momentum and slows down a little bit here, which is something that we expect as well. So generally those results look pretty good. We can do some vectors as well, which will help illustrate the flow a bit. So we're going to do vectors of velocity on this surface, on all the interior surface parts. So this is pretty cool. We can see little velocity vectors. So we can see how the air is heading straight to the airfoil, and then the vectors show that it migrates around, which is what we would expect. We don't want to see anything flowing through. We should also be able to see the profile of the boundary layer, which we can, which is pretty cool. So the no slip condition, we should have a velocity of 0 at the wall. The lowest on the scale is 0.2, so we're pretty close to that. And we can see the profile going down to almost 0 and then slowly increasing up until we have the free stream, which is what we would expect too. So that's pretty good. I'm happy with those results. We could also look at the at some plots. So we can do an XY plot of the data that we have. We can look at the pressure coefficient over the aerofoil wall. So you can see up here we almost get that 1 for the stagnation point, which is correct. And then we get the negative pressure associated with that accelerated flow here, and then we start to get a bit of positive pressure coefficient towards the tail where we started seeing the flow slow down a bit. Because it's a symmetric aerofoil, there are 2 curves here, and they're both just on top of each other because they've got the same values. Once you put it at an angle of attack, which we'll do later, you'll be able to see how that works a little bit better. We can also, so I spoke about the wall Y+, we can check that here on the airfoil wall. So we want a wall Y+ of around 1, and we can see we're between was it 0.4 something here and 0.5 there, with a bit of fluctuation. So we've achieved that more or less. Ideally you would just have a straight line across here, but to get that in actuality is quite difficult, so not too disappointed with that. So that's pretty much what we can do on that front. We can also use the CFD post, which comes with Ansys. Let's wait for that to open. Oh, what's happening? Trying to think about it. How about we just go back to Fluent and look at a couple of other things. We could also do some path lines here. I was trying to export. It needs to export the results before it can put it into post, so that's what we're waiting for. So it looks like post is open, so I just won't worry about this anymore. For some reason it does that, I don't know. So you can pretty much do exactly the same stuff in here. You got contour. You select that we want to have it on the symmetry. Now we can look at pressure here and apply. If we get rid of the wireframe, you can see it a bit better. Oh, that's rotating. So again, this is pretty much exactly what we saw in Fluent before. You can add increased number of contours, so you'll get a bit better resolution of some things. Again, we can do that with velocity or any of these variables really. I won't go through that because it's pretty straightforward. One thing that is probably interesting is if we draw a line. So we've got to give the x, y, and z components. So we'll give -5, y, we'll just give 10, 0, and then -5, -10, 0. We'll put 550 samples on there. So we should see a line appear here now. Somewhere. X, Y, Z, Y, line. And what we'll do is we will add some streamlines from that line. So we will go on line 1, maximum number of points 50. Get rid of the contour. So we can see here that we've added some streamlines. No, it doesn't seem to be. Where's the wireframe? So if we add the wireframe in, we can see the airfoil again. If we change this number here and we put in an added number of streamlines, hopefully get a bit of better resolution of the flow over the airfoil. So it will go even further than that. Let's go 500. Y streamline 500. Apply that. So we can see here the flow. It's colored by velocity. So again, you can see the flow accelerating around the airfoil where you have some red. So those are just some basic things that you can do in here. This isn't really my preferred post processor. We use TechPlot. But yeah, that's just generally how you can post process the results and investigate whether or not you're happy with the solution. So I'll leave it there. I will be making some more videos about this particular case. I'm going to look at some unstructured mesh and compare it to this structured mesh. I'm going to run it over over an angle of attack range and see how the results come out compared to published data. So stay tuned, there'll be more videos to come.